So welcome to this next tutorial on electric circuit analysis, that is the tutorial 8, Norton's theorem. In the previous tutorial we were discussing the Thevenin's theorem, and here in Norton's theorem we will have the concept remains the same as like Thevenin's theorem. So little bit overview of the Norton's theorem, let us see, so that how you will be solving the problem you will able to know that. Okay, so what does Norton's theorem suggest? If you have any complex circuit, okay, complex circuit means a circuit which is having too many sources or the passive elements like that, then in that case you can reduce the circuit into a simple equivalent circuit consisting of a current source which is known as the Norton current in parallel with a resistance which is known as the Norton resistance, R Norton. Okay, so what is the Norton current and what is the Norton resistance that you have to calculate? Norton resistance is simply the Thevenin resistance that we have calculated when we have studied the Thevenin's theorem. So Norton resistance and Thevenin's resistance are same thing, which is basically the equivalent resistance when the terminal is open circuit. Okay, so Norton resistance and Thevenin resistance are the same thing. Whereas the Norton current is basically the short circuit current that is at the terminal AB. So when you have the load terminal, you short circuit that terminal to find the Norton current. When you find the Norton resistance, then all independent sources need to be turned off. Independent sources need to be turned off. Independent source just means that if you have a voltage source or a current source which is independent, that you need to turn off. However, dependent source will not be turned off. So dependent source will not be turned off. Only independent sources will be turned off. And the Norton and Thevenin's are related to each other. For example, if you write what is the value of R Thevenin. So R Thevenin is equal to R Norton, which is equal to voltage by current, right? So what is the voltage? Voltage you can write the Thevenin's voltage, and the current you can write the Norton current. So there is a direct relationship between the Norton circuit and the Thevenin circuit in accordance with source transformation. Because in Thevenin's theorem we have studied that if you have a voltage source V Thevenin, which is the equivalent voltage source at the terminal AB under the open circuit condition, it is in series with a resistance which is known as R Thevenin. If we observe these two circuits, Norton circuit and the Thevenin circuit, both are related to each other from the source transformation concept. So we have studied the source transformation. Source transformation simply means that voltage source will be converted to current source by appropriately positioning the value of the resistance. So this is the concept of Norton's, which is related to Thevenin's, and then we'll solve the problem. So the first problem is a very simple problem. We'll start. Determine the Norton equivalent current and resistance at the terminal AB. So wherever you need to determine the variable, that is considered the terminal or the load terminal RL. So here you have to find the current, which is basically the Norton current, and the resistance, which is the Norton resistance. So that two quantities you have to find, and then you can draw the equivalent circuit. So let us see how to find the R Norton and I Norton and then draw the equivalent circuit. So in order to find the I Norton, we will be short circuiting the terminal AB. So short circuit the terminal AB and determine what is the current which is flowing through terminal AB. That will be the Norton current. And then you can apply any concept, whether it is a KVL or KCL, to determine what is the current which is flowing here. That is the short circuit current. Now if you apply the KCL at node A, if you treat this one as node A, you apply the KCL, all the current which is meeting the node, either entering or either leaving, we can write the equation, that is summation of all the current at a particular node, that is A, is equal to 0. So here we have the current distribution, Norton current, 2 ampere current, and one current which is flowing this side, that is I1, right? And we can write this equation and find out what is the value of the Norton current. Once we have found out the value of Norton current, now we will be calculating the R Norton, that is the open circuit equivalent resistance at the terminal AB. So when we see towards the terminal, what is the equivalent resistance, that is known as the R Norton. Now here we need to remove the sources. We have to turn off the sources. So voltage source will be turned off using a short circuit. Current source will be turned off using open circuit. So here we have a voltage source which is short circuited. Here we have a current source which is open circuited. Now you can find the value of R Norton. So R Norton simply is the equivalent resistance, which is equal to 24 ohms in this particular case. So we have obtained the value of I Norton and we have obtained the value of R Norton. Now the equivalent circuit we can draw, that is I Norton in parallel with R Norton, and then we will be having the terminal AB. So this is the terminal, and here you have I Norton and R Norton, whose magnitude we have calculated. So the problem was very simple. Now let us see some other problems. So problem 2, you have to determine the voltage V0 using the Norton's theorem. So V0 is the voltage across the 1 kilo ohm resistor. Okay, what is the potential drop across 1 kilo ohm resistor? That is V0. So wherever the variable we need to determine, that part of the element is considered as the load terminal. Okay, so we can consider this one as A and this one as B as the load terminal, because we need to determine the variable V0 in the circuit. Now we have to divide the circuit into two parts. So this part of the circuit is basically the fixed part of the circuit, whose Norton equivalent current and resistance we have to obtain, and this is the variable part of the network or the load terminal. So this is the variable part which will be reconnected once we obtain the value of the Norton circuit. So let us see how to do this and how to obtain the value of I Norton here and R Norton to draw the circuit. So first we will calculate the value of R Norton at the terminal. So we have to remove the variable resistance or the load resistance from the network. So first you remove the load resistance with an open circuit, and towards the terminal, inside the terminal, you have to see it. Now you disconnect the independent sources. So we have a 36 volt independent source and 3 milliampere current source independent source. So voltage source will be replaced with a short circuit, current source will be replaced with open circuit. So we have short circuited the voltage source and open circuited the current source. Now we are in a position to determine the R Norton, which is basically the equivalent resistance. So if we see this circuit, we find that 12 kilo ohms and 24 kilo ohms are in parallel, and that is in series with 2 kilo ohm, and then it is in series with 10 kilo ohm. So we can apply the series parallel concept that we have studied to find the value of R Norton. So R Norton is basically the equivalent resistance, that is 20 kilo ohms. This is similar to R Thévenin, which we have calculated in the Thévenin's theorem. So 20 kilo ohm is the value of R Norton. Now we have to obtain the I Norton. So in order to obtain the I Norton, the load resistor is short circuited. So RL, which is the load resistor, is basically short circuited. So we have the short circuit current which is flowing here, that is known as the Norton current, that we need to determine. Okay, keeping the other part of the circuit as it is. So we have a 36 volt source and 3 milliampere current source and other resistances we have. So we have to determine the value of I Norton. The value of I Norton, that is the short circuit current, we can determine by different techniques, whether it is a KVL, KCL, superposition, source transformation, any theorem we can apply it. Now, if we apply superposition theorem, then let us see how to find the value of I Norton. So superposition theorem we have studied in the lecture class, that Superposition theorem will have one source which is active at a time. So we have a voltage source and we have a current source. And one source you keep active at a time, and then you determine the corresponding response at the terminal, which is the load terminal. So you can find the Norton current as the sum of all the responses due to individual source. So you have IB, that is the current at the terminal due to source 1, and II is the response due to the source 2. So we have a voltage source and we have a current source. We will keep one source active at a time. So when we keep the voltage source active, then the current source will be open circuited. When we keep the current source active, then the voltage source will be short circuited. So let us see how to do this. Now you keep the voltage source active at a time. So we have a 36 volt and 3 milliampere. I will keep the 36 volt active. So it means that 3 milliampere has to be removed from the network, which is removed using the open circuit. So we can open circuit these two terminal of the current source, and then we can determine the value of the current which is flowing at the load terminal, which is written as I1. Okay, now these again can be calculated. I1 can be calculated using KVL, KCL or other techniques. Let us apply the source transformation here. Okay, if we apply the source transformation, so in this particular problem we will be studying the Norton's theorem, the superposition and the source transformation. All are combined in this particular problem. So source transformation, if we apply, then we see that 36 volt and 12 kilo ohm resistor can be replaced with a current source in parallel with a resistance, where the current source is basically voltage by resistance. So we have 36 volt divided by 12 kilo ohms, which will be giving us 3 milliampere as the current, and the resistance is 12 kilo ohm, which is coming in parallel. Now it is very easy because we have series parallel combinations, like these two resistors are in parallel and which is in series with 12 kilo ohm resistor. So we can do that to find the value of the current. Okay, so what we can do is that we can find the equivalent resistance of these two network, or the resistance, which is equal to 8 kilo ohms. Now our circuit will be like this. We will be having a 3 milliampere current source, one resistance which is of 8 kilo ohms, which is the parallel combination of 12 and 24, and then we have a resistance which is equal to 12 kilo ohm. Right? Now we have to determine what is the current I1 flowing here. It means the same current will be flowing here also, that is through the 12 kilo ohm resistor. So we can apply the current division rule. Now you see how we are moving from one theorem to another. We have started from Norton's theorem, then moved to the superposition, then source transformation, and now the current division. So using the current division rule, we can find what is the current which is flowing here. That is the source current, which is 3 milliampere, multiplied with, in the numerator you will have the resistance which is in parallel, that is 8 kilo ohm, divided by the sum of the resistance, that is 8 plus 12. We will get 1.2 milliampere as the current which is flowing when only one source, that is 36 volt, is active. So from the superposition theorem we have find out my first case, that I1 is equal to 1.2 milliampere. Okay, now my second case will be there, where I will keep the current source active and the voltage source will be removed. So if the voltage source is removed, I will be removing this with a short circuit, and I will keep this current source active, and I will try to determine the value of the current that is sorted here. What is the current I2 that is flowing? Okay, now this is in accordance with superposition theorem. So we see that this left part of the circuit and right part of the circuit, we can do the series parallel combination of the resistance, and we will have a simple circuit where we will be having a current source, one resistance this side and one resistance this side, and we will be able to find what is the current I2 which is flowing here. So this is with the series parallel resistance. So current I2 that we will be getting is minus 1.5 milliampere. This current which is flowing minus 1.5 milliampere. So we have two currents due to the two sources of superposition. Then we can find the Norton current by adding the two currents, which gives to be minus 0.3 milliampere. Now the Norton equivalent circuit is basically a Norton current in parallel with a resistance, that is R Norton. Now the variable resistance, which is the load resistance, will be reconnected to the equivalent circuit which is obtained from the Norton theorem. Okay, so I Norton and R Norton we have obtained, and the value of RL that we have removed, now we will be reconnecting it, that is 1 kilo ohm. Now it will be easy to determine the potential which is across the 1 kilo ohm resistor, which is nothing but the voltage across this. So if we apply the current division rule and try to determine what is the current which is flowing here, I take this current to be Ix. So Ix is the current which is equal to I Norton multiplied with the parallel resistor, that is 20 kilo ohm, divided by 20 plus 1, that is the equivalent resistance. So I will find what is the value of Ix. Now the voltage V0 that we need to determine is basically Ix, that is the current, multiplied with the resistance, that is 1 kilo ohm, and that we need to determine. So here we will be getting the voltage as minus of 0.285, where minus sign just simply means that the polarity will be reverse for what we have seen. So this problem is solved. Problem number 2, where we have applied the Norton's theorem, superposition theorem, source transformation, current division, voltage division rule. Okay, so this problem covers many concepts at a time. Problem 3, you have to determine the Norton equivalent current and resistance at terminal AB. So you have a source 120 volt and there is a source of 3 ampere. Both are independent voltage and independent current source. Let us try to determine the Norton current and Norton resistance at the terminal AB. Okay, so what we do, first we find the Norton resistance. So short circuit the voltage source, open circuit the current source, and redraw the circuit into its format to obtain the R Norton. So what we can find that the 20 ohm resistor and 40 ohm resistor are in series, which is in parallel with 12 ohm resistor. So we'll get 10 ohms as the value of R Norton. So this is what we have found out. Now we determine the Norton current. So to determine the Norton current, we short circuit the terminal AB. So you short circuit the terminal AB of the original circuit. That will be the Norton current which is flowing. Now you can apply different theorems, KVL, KCL, as superposition, source transformation, any theorem you can apply to find the Norton current. Let us see how to do that. I will be applying the source transformation. So this part of the network I can reduce into a simpler format. That is, we can have a voltage source in series with a resistance. So voltage source is nothing but current multiplied with resistance. So we have 2 into 40, that will be equal to 80 volt. 80 volt will be in series with 40 ohm. So here we have applied source transformation. Now we have only one network. We can apply the Kirchhoff's voltage law or the mesh analysis to determine the value of the Norton current. So you apply the KVL, that is algebraic sum of all the voltages in a closed loop is 0. You will be getting the Norton current as 0.66 ampere. So we have obtained the value of Norton current and the Norton resistance. Problem 4, determine the current using the Norton equivalent circuit. So you see the current I we have to determine, which is flowing through 5 ohm resistor. So wherever you need to determine the variable, that will be your load terminal RL. Okay, so you will be having A and B as the load terminal that you need to remove from the circuit and determine the Norton resistance and Norton current. So let us see how to do that. Once we remove this 5 ohm resistor, which is basically a load resistor, and then we disconnect these independent sources, that is, we will be short circuiting the voltage source and open circuiting the current source. What we are getting? So if we open circuit this will be removed from the network, this will be short circuited, then this part is open circuited. Sorry, this part is open circuited because we need to find the value of the resistance, okay, and we have to see the circuit from this end like this, okay. So if we are seeing from this end to find the R Norton, we have 6 ohm and 4 ohm which are in series to each other. These 6 ohm and 4 ohm will be in series. So we will be able to determine the R Norton as 6 plus 4, that is 10 ohms. So you have a 6 and 4, and that combination will give 10 ohms as the R Norton. Now, if I need to find the I Norton, what I am going to do, the load resistor I will be short circuiting. So this part is short circuited, and then what I can do is that I can make the things to be simple by applying some source transformation, and then I can determine the short circuit current. Okay, so if I'm sorting this current source will always be sorted. So we will be having like this one circuit where we have the 2 ohm resistor, 2 ohm current source, we have 4 ohms resistor, we have a 6 ohm resistor, and we have a 12 volt voltage source. So this is the new circuit that we have got it. So can we determine what is the current, Norton current, that is flowing? So these you can apply the KCL to determine the voltage here. What is the voltage at this particular node? So you can apply the summation, all the current which is meeting at the particular node that we have written V is equal to 0. We can find the potential of that node, that is 9.6 volt. This is in accordance with Kirchhoff's current law. Now once we have obtained the voltage here, I can find that what is the current which is flowing this side, because that is the Norton current. Whatever the current is flowing this side, that is basically the Norton current. So Norton current I am getting as minus of 0.4 ampere. So I have got the Norton current and I have got the Norton resistance for this network. Now once I got the value of Norton current and Norton resistance, I can reconnect the 5 ohm resistor which was short circuited. So we will be combining the remaining part of the circuit. So since we were determining this side, so I have to connect these two part of the network, that is the right hand side, to the Norton equivalent circuit. So once we connect that, I can determine what is the current which is flowing through the resistor 5 ohms. So that can be done by improving the circuit. So here you have 4 ampere. This one is 5 ohms through which the current you need to determine. And then you can have the Norton current and the Norton resistance, which we have the equivalent circuit. So we can determine from this circuit what is the current which is flowing here. So this current, you can apply the current division rule to apply that, because we are having two resistance which are in parallel and two sources of the current, which will be 4 minus 0.4, because the Norton current is 0.4 and we have a negative sign, so the direction is like this. So we can determine the current, that is 2.4 ampere, which is flowing through 5 ohm resistor. So in this way we can solve the problem using the Norton's theorem. Okay, this is the final problem. Find the Norton equivalent circuit. Okay, so what is the difference in this problem? You have a current source, that is 2i1, and this is the dependent source. Okay, so we have one dependent source now. Now let us see how to do this type of problem, because we do not have independent source in the circuit, we have dependent source in the circuit. And as I said you that whenever you are finding the value of R Norton, you are not going to replace the value of the dependent source. It is only the independent source that has to be removed from the network. So how to do that in this problem? Okay, so first we apply the Kirchhoff's current law at the two node V1 and V2 to determine the potential, keeping the node to be sorted, because we need to find the Norton current, which is basically the short circuit current at the terminal. Okay, so here we have a dependent source and we can apply the KCL at node V1. This is the node V1. We can write the KCL equation, algebraic sum of all the current to be 0 at the node V1. So this is the KCL equation. KCL equation at node V2, we can write that algebraic sum of all the current at the node V2 is equal to 0 in accordance with this equation. So all the current which is meeting and all the current which is leaving, that all current we have to add up to form the KCL equation. So I find that the V1 is my variable, V2 is the variable, and I1 is the variable. Three variables in two equations. One more equation is there where the current I1 that is flowing, I can write V1 minus V2 by 2. So we have three equations and three variables that we need to find. So if we solve these three equations in three variables, I can determine the value of V1 and V2, which is the node potential, V1 and V2. Now, my target was to find the short circuit current, that is the Norton current. And then we can apply the KCL equation to find the Norton current, because this is at 0 volt. So we can apply the KCL here at this particular node to find the Norton current. So I will see that on applying the KCL equation, Norton current is also coming to be 0 ampere. So because the target was to find the Norton current, I have used the KCL to find this potential V1 and V2. So my first objective is clear, where I need to find the Norton current, which is 0 ampere. Now what about the Norton resistance? So Norton resistance, you know that whenever you have a dependent source in the circuit, you can't find the R equivalent simply by series parallel concept. In that case, you at the terminal you have to connect the known voltage source or a known current source. If you apply a known voltage source of 1 volt, you can obtain what is the corresponding current which is flowing from this voltage source. So if I divide that voltage and the current, I will be getting the value of the resistance, that is the Thévenin resistance or the Norton resistance. Both are the same thing. Okay, so Norton resistance is coming to be 3 ohms. Now I can redraw the circuit with a Norton current. So Norton current was 0 ampere and Norton resistance is 3 ohms. So my Norton equivalent circuit is this one, where the current source is 0 ampere. It simply means that it is a open circuit. So this is the Norton equivalent circuit. So we have solved few problems on Norton's theorem, which comprise of both the dependent source as well as independent sources.